Few people know that antibiotics, the medicines that suppress common illnesses such as coughs, fevers, and sore throats, as well as more difficult diseases like tuberculosis and meningitis, are actually a type of selective poison. They target tiny enemies called bacteria and defeat them. Thanks to this property, antibiotics have been praised as the miracle of modern medicine, saving millions of people from diseases once considered incurable. But problems arise when such a powerful weapon is used improperly, leading to dangerous consequences. What was once considered a miracle drug can become useless, or even counterproductive. At that point, even a small wound on the hand can lead to sepsis, and antibiotics will no longer be a weapon against bacteria. One issue quietly creeping into global healthcare is antimicrobial resistance, AMR. In simple terms, antibiotic resistance is the condition in which bacteria become stubborn, begin to evolve, learn to survive, and more strains become unafraid of antibiotics. This poses a serious threat to public health. According to the World Health Organization, about 1.6 million people die each year due to antibiotic resistance, and this number could exceed 10 million by 2050 if no timely action is taken. What's even more frightening is that we are not talking about the distant future. Antibiotic resistance is happening right now, including during pandemics such as H1N1 and especially COVID-19, who once reported that more than 75% of hospitalized COVID-19 patients worldwide were prescribed antibiotics, while fewer than 10% actually needed them. A lack of awareness, combined with the habit of self-diagnosing and buying medicine without a prescription, is turning the public into a link in the chain of antibiotic resistance's spread. So how can we reduce the dangers of antibiotic resistance? Let's join author Baram at Spy Room in Going Back in Time to explore the origin of antibiotics and the reasons why antibiotic resistance has become so common. The history of antibiotics. The story begins one day in 1928 in the laboratory of Dr. Alexander Fleming. A coincidence occurred that changed the course of medical history. At the time, Dr. Alexander Fleming discovered a strange mold capable of inhibiting the bacteria Staphylococcus aureus, a dangerous destroyer more commonly known as the golden staph, which can cause infections in humans. The mold Fleming found belonged to the genus Penicillium, and from it, penicillin, the world's first antibiotic, was discovered. Although it was found in 1928, it wasn't until the early 1940s, thanks to the talent and perseverance of two scientists, Howard Florey and Ernest Boris Chain, that penicillin was mass-produced and officially used in medicine. During World War II, penicillin was like a savior, saving thousands of wounded soldiers by treating infected wounds and significantly reducing the mortality rate. This success paved the way for a race to discover new groups of antibiotics, such as streptomycin, tetracycline, erythromycin, and cephalosporin, ushering in a new era for medicine at the time. These advances not only expanded the scope of treatment, but also diversified the mechanisms by which antibiotics act on bacteria. The mechanism of action of antibiotics. Antibiotics are compounds capable of killing or inhibiting the growth of bacteria through various mechanisms. Each type of antibiotic is usually effective against only one or a group of specific bacteria, with its own mode of action. Therefore, identifying the exact type of bacteria causing the disease and selecting the appropriate antibiotic is crucial in treatment. A common way to attack bacteria is to destroy their protective cell wall. Some well-known antibiotics, such as penicillin and cephalosporin, often use this method. Penicillin blocks essential enzymes that bacteria need to build their cell walls, and when these building agents are defeated, the bacteria burst and die. Interestingly, this mechanism is very effective against rapidly growing bacteria, like catching them right when they're building a house but haven't laid the foundation yet. That's why this group of antibiotics tends to wipe out the weaker bacteria that are actively dividing first, and then take care of the tougher ones lying dormant and waiting for the right time. This explains why the process of killing bacteria with antibiotics usually follows the sequence of weak first, strong later. This is also why antibiotic treatment cannot be stopped early just because the symptoms have improved. In addition, there is another group of antibiotics, such as fluoroquinolones, that are also very powerful. But instead of breaking down the cell wall, they aim straight at the core, the DNA of the bacteria. To grow and reproduce, bacteria need to replicate their DNA. Think of it as photocopying documents to distribute to the next generation. To succeed in reproducing, bacteria need two assistants: the enzymes DNA gyrase and topoisomerase 4, which help unwind, cut, and paste DNA. The fluoroquinolone group attacks right when they are cutting the DNA, holding the cut open so it cannot be rejoined as before, causing the DNA strand to completely break. Once the DNA is broken in two, the bacteria have no way to survive. Tetracycline, however, does not attack head-on by breaking the cell wall or targeting the genetic core. Instead, it strikes at the bacteria's most basic source of life, the ability to produce protein. A bacterium is like a small factory, and all its activities depend on protein. To make protein, amino acids must be assembled in the correct sequence. This process takes place in the ribosome, the assembly line of the bacterium. Tetracycline doesn't destroy this assembly line, but instead blocks the entry point for the raw materials. When the door is locked, the bacterium cannot synthesize protein, and thus cannot live or reproduce. Tetracycline doesn't directly kill bacteria, but weakens them over time until they eventually die. That said, if it encounters already weak bacteria or is used at a strong enough dose, it can still finish off the opponent. Interestingly, the effectiveness of tetracycline can vary depending on the bacterial species. Some are knocked out quickly, while others only slow down but still manage to struggle on. This is why it is essential to use the right antibiotic at the right dose and for the full prescribed duration. If not, bacteria that are not completely killed will have a chance to fight back and evolve to become stronger. This is why doctors usually prescribe antibiotics for a period of 7 to 14 days, no more, no less. This duration is not arbitrary, but has been drawn from many years of experience and thousands of studies. Each case, infection site, and patient's condition requires a different treatment length. One thing is certain: completing the prescribed course is always better than stopping midway. Although antibiotics are highly effective, if used improperly, they can cause serious side effects such as digestive disorders, rashes, and in rare cases, anaphylactic shock, which can be life-threatening. At the same time, improper use of antibiotics increases the risk of bacteria evolving to evade the effects of the drugs. Antibiotic resistance, the other side of the pride of modern medicine. In a famous speech after receiving the Nobel Prize in Medicine in 1945, Professor Alexander Fleming, the man who discovered penicillin, warned humanity about the growing danger of careless antibiotic use. He said that those who misuse penicillin thoughtlessly would bear moral responsibility for the death of a person infected by penicillin-resistant bacteria. His warning, issued nearly a century ago, remains just as relevant today, as reality has shown that when antibiotics are overused, the weapon once hailed as a miracle of medicine can become useless, or even counterproductive. The biological nature of bacteria and the mechanism of antibiotic resistance. To better understand how antibiotic-resistant bacteria develop, it is first necessary to grasp the biological nature of bacteria. Under ideal conditions, a single bacterium can double into 2 every 2 to 30 minutes. Within just a few hours, one original bacterium can turn into billions. Each time this happens, the entire genetic material, DNA, is replicated. During this copying process, natural errors, known as mutations, can occur. Although the mutation rate per base pair is very low, only about 1 in 10 billion, when bacteria multiply into millions or billions of cells in a short time, the number of accumulated mutations can become very large in just a few hours. Some of these mutations may help bacteria resist the effects of antibiotics. Beyond mutation, bacteria can also exchange genetic material with each other through a mechanism called horizontal gene transfer, which includes transformation, taking in DNA from the environment, conjugation, transferring DNA through direct cell-to-cell contact, and transduction, transferring genes via viruses. Thanks to these methods of exchange, resistance genes can spread very quickly, not only within the same species, but also between different species of bacteria. What does this mean in practice? It means you might use one type of medicine to treat bacterium A, but then bacterium B also becomes resistant, even though it was never directly exposed to that medicine. Over time, this leads to the emergence of superbugs, types of bacteria for which no existing antibiotic is effective. Causes of antibiotic resistance. Improper use of antibiotics, such as buying medicine without a prescription, not following the doctor's orders, or stopping treatment halfway as soon as symptoms improve, is the fastest route to the development and spread of drug-resistant bacteria. During treatment, antibiotics generally tend to quickly kill off the weaker or more common bacteria, those microorganisms that are most sensitive and easy to eliminate. However, within any bacterial population, there are always a few individuals with biological traits that allow them to tolerate antibiotics better. If a patient does not continue treatment for the full prescribed duration, such as stopping after 3 or 4 days because they think they're cured, these hard-to-treat bacteria will remain in the body. With no competition from the sensitive bacteria that have already been eliminated, they will multiply rapidly and be nurtured longer in the body's environment. Their chances of mutating or acquiring additional resistance genes from other bacteria via horizontal gene transfer will only increase. This process unintentionally becomes a survival test. When antibiotics are introduced, the weaker bacteria are eliminated, while the stubborn ones with resistance genes survive, multiply, and pass those genes on to future generations. Over time, the entire bacterial population is gradually replaced by resistant individuals. The environment has essentially selected for the strongest. Eventually, this leads to the emergence of bacterial strains that are not only harder to treat, but can also spread within the community, reducing the effectiveness of antibiotics that were once highly successful. Not to mention, many people have the habit of taking antibiotics at the first sign of a cough or runny nose. Using medicine in this way can sometimes kill off beneficial bacteria in the body, especially in the gut, which harbors an entire ecosystem that aids digestion, immunity, and disease prevention. A report by the World Health Organization, WHO, shows that about 50% of all antibiotics used worldwide are inappropriate for their intended medical purpose. This is one of the main factors contributing to the rapid increase of antibiotic resistance globally. Few people realize that each human body contains its own unique ecosystem of microorganisms, including countless symbiotic bacteria that help with digestion, regulate immunity, and protect against pathogens. When antibiotics are overused, they kill not only the harmful bacteria but also these important allies. When the microbiome becomes imbalanced, the body weakens, creating an opportunity for the minority of resistant bacteria to rise, multiply, and dominate. Research published in Nature Reviews Microbiology shows that indiscriminate use of antibiotics can disrupt the microbiome for extended periods, from several months to many years after treatment has ended. This means the consequences go beyond simply failing to cure an illness. They can have long-term effects on both individual and community health. Therefore, through uninformed habits such as self-medication or over-reliance on instant results, people themselves are inadvertently fueling the widespread evolution of antibiotic-resistant bacteria. If behaviors and awareness do not change, the antibiotics that once saved humanity will become useless in the not-so-distant future. Causes of improper medicine use. One of the reasons antibiotic resistance is becoming increasingly severe lies in the way people use medicine, specifically, using it incorrectly at the wrong time and for the wrong purpose. What might seem like a simple matter actually stems from a lack of knowledge, social habits, loopholes in control systems, and even factors outside the field of medicine, such as livestock farming. First, many people still confuse illnesses caused by viruses with those caused by bacteria. Symptoms like colds, sneezing, and sore throats are often caused by viruses, yet they are frequently treated with antibiotics. However, these drugs are completely useless against viruses. The result is that the illness is not cured, while beneficial bacteria in the body are also killed, creating opportunities for resistant bacteria to develop. In addition, stopping treatment early, right after feeling better instead of completing the full prescribed course, is like throwing fuel on the fire, accelerating the spread of antibiotic resistance. Next is the habit of self-diagnosis and buying medicine without a prescription. A global systematic review and meta-analysis showed that the prevalence of antibiotic self-medication, ASM, without a doctor's prescription is about 43% worldwide. The problem is that patients cannot truly know what illness they have or which medicine is correct, making the risk of using the wrong drug or wrong dosage extremely high. The issue also lies in the distribution system. Although the law requires a prescription for antibiotics, in reality, many pharmacies still sell them freely to anyone who asks, whether for profit, due to lack of oversight, or simply because the seller does not understand the long-term consequences. The WHO has warned that the sale of antibiotics without prescriptions remains widespread in many developing countries. Even in hospitals, places assumed to be safe zones, the prescribing of antibiotics is not always done correctly. Many doctors, lacking test results or simply wanting to be cautious, choose to prescribe broad-spectrum antibiotics. Added to this is pressure from patients and their families, which can sometimes force doctors to comply with demands rather than make decisions based solely on medical expertise. Finally, there is an area that receives little attention but is extremely important: agriculture. Antibiotics are used not only to treat sick livestock, but also to promote faster growth. This creates an ideal environment for bacteria to learn how to resist antibiotics, and these resistance genes can easily jump to humans through food, wastewater, or direct contact. From this, we can see that everyone, from the general public, to pharmacies, to hospitals, to farms, is contributing to a crisis known as antibiotic resistance. To combat it, it is not enough to simply urge people to stop taking antibiotics recklessly. Solving this problem requires close coordination between public awareness campaigns, stricter regulations on drug management, and equally importantly, changes in how the agricultural sector uses antibiotics, if we want to avoid facing untreatable superbugs in the near future. Recommendations for the public. According to the recommendations of the World Health Organization, the use of antibiotics must be strictly controlled under several key principles to protect public health and slow the progression of antibiotic resistance. The first and most important principle: only use antibiotics when prescribed by a doctor. Do not rely on hearsay, do not self-diagnose through the internet, and do not assume that the medicine you took last time, because it seemed to work, can be used again. Only a doctor has the knowledge to determine whether an infection truly requires antibiotics, and if so, which type, what dosage, and for how long. Second principle: once you start, you must complete the full course. Many people stop after a few days when they feel better, but the bacteria are not yet completely dead. They are merely dying and will come back stronger if any are left behind. Stopping treatment midway is the fastest way to create a new generation of bacteria that are both tougher and resistant to antibiotics. Third principle: never share medicine. Antibiotics are not candy, and they are certainly not traditional remedies to be passed around freely. Two people may both have a fever and sore throat, but that does not mean they have the same type of bacteria. Moreover, everyone's body responds differently. Using someone else's medicine can not only fail to cure you, but also increase the risk of complications or give bacteria the opportunity to develop resistance genes. Fourth principle: don't hold on to leftover antibiotics. Medicine left over from a previous treatment may not be enough for a full course, may not be appropriate for the current illness, and could even have degraded if stored improperly. Reusing them will not help you recover and may even cause harm. Finally, always inform your doctor if any problems arise. During antibiotic treatment, if you experience symptoms such as rashes, diarrhea, or nausea, do not try to endure them or find your own remedy. Report them to your doctor immediately so your treatment can be adjusted. Every body reacts differently, and no one should gamble with their health when it comes to medicine. If you enjoyed this video, please like and share to support us. Don't forget to hit the subscribe button and the bell icon so you won't miss any of our future videos. Thank you for listening. See you.